Hello, my name is Marisa Cantarino, and today I'll talk about this paper by Michael Chubb and Amy Wilkinson called Pathological Foliations and Removable Zero Exponents. I will focus on the pathological foliations part, and we will get it as a perturbation of a kind of map that is called partial hyperbolic. And this condition of having pathological foliations will be robust. So to start, we are working on a m-dimensional manifold that is compact and smooth. And F is a CR diffeomorphism with what we call a dominated splitting. That is defined by the fact that here we have more expansion of vectors than here, and here we have more expansion of vectors than here. This is the dominated splitting. And partial hyperbolic is a special case in which one of these two directions, ES or EU, are non-trivial. And one EU is uniformly expanding and ES is uniformly contracting. In our examples, both of these directions will not be trivial. And they are DF invariant because the action of the derivative on the tangent bundle preserves this decomposition. This is what we call partial hyperbolicity. And then, what is a foliation in this context? A foliation in our dynamical context is the following. It's a partition of the manifold, so we are in the manifold M, and we make a partition W of this manifold into CR submanifolds of dimension K. This dimension will be the dimension of the foliation. And this partition has to obey the following conditions. For each x on the manifold, there is a local chart that it's parameterized by the ball of dimension K times the ball of complementary dimension. So here in the picture we have a ball of dimension K and another ball of complementary dimension to the open set U that contains X in such a way that this chart takes this pink line here to the pink leaf. This is the leaf. No, this is the notation we use. If the foliation is W of a point, or we call this point Y, is the leaf of the foliation that contains that point. So this is Wy times the neighborhood U. So the intuition of this is the following. Each leaf is CR, and these leaves are stacked continuously. So the formal definition is there is this local chart, and the function that takes the point 0, 0 to x, this phi, also takes these horizontal lines into leaves, local leaves of the foliation, in such a way that this function, oh, I'm sorry, here is phi. Phi is CR along the vertical lines, and it is continuous along the horizontal lines. This may seem like a weird definition if you already saw a definition of foliation from geometry, but this is the kind of leaf that arrives in this context of partial hyperbolic maps. And this is a theorem that says that if the dimension of the unstable, or everything here works for the unstable with the green comments here in the statement. So I will announce it for the unstable direction. If the unstable direction is non-trivial, that is, in your dominated splitting, you have a direction with uniform expansion of vectors on the tangent bundle, then there is a unique foliation that we call unstable foliation that is invariant by our dynamics. It's continuous. Its leaves are CR, like in this definition above. And the dimension of the leaves is the same dimension as the distribution on the tangent bundle. These leaves have this distribution as the tangent directions on each point. And for each point, the leaf that contains its point is uniformly contracted by the inverted dynamics. And if we are looking to the stable directions, they are uniformly contracted by the forward dynamics. And then, so here we have unstable and stable foliations. But our tangent space is decomposed in 3 subbundles. And if EC is non-trivial, that is our case here, we don't know in general if this direction also integrates to a foliation. So we say that F is dynamically coherent if the center stable direction, that is the sum of the stable and the center one, if it's in the center unstable direction, that is the sum of the center and the unstable one, are uniquely integrable. So in this case, this is the same as saying that there are unique foliations that are tangent to this direction, and this implies that EC is integrable, because we just have to take the intersection of the center stable and the center unstable leaves to get the center one. And if EC is uniquely integrable, we also have dynamical coherency, because we can take this center foliation, and for each point on the center foliation, we take the stable one passing through it. And when we make this union, you get the center stable leaf, and the same for the unstable one. This is not necessarily true in general for partial hyperbolic maps, but in our context, it will be true. So in our case, the dynamical coherence is given by the following. This result gives not only the existence of the center foliation, but it also gives us how are the topology of its leaves. So if the map has a plaque expansive central foliation, then this map, together with this foliation, the center foliation, is structurally stable. This is true, for instance, if the foliation is C1. So if the foliation is C1, it is plaque expansive. In particular, we can apply this theorem to say that the center dynamics, the map together with the center dynamics, is structurally stable. This means that this map with this center foliation are preserved topologically under perturbations. The precise meaning is the following, this definition here. WC, the center foliation, is structurally stable if you take a nearby map G, there is a homeomorphism that conjugates the leaves. So it takes the leaves of F to the leaves of G of corresponding points, and it's isotopic to the composition of H. So this is a topological conjugacy between the dynamics on the leaves and the leaves themselves. And this is true in our case because, as we'll see later, our center foliations will be smooth. So we can apply this theorem here, and we have this stability. So I'm just announcing it now for using later. Now I'm going to talk about measurable properties of foliations. And this theory here is more general, is for any partition on a measurable space. So I'll give some definitions. A disintegration of a measure with respect to a partition is a family of probability measures defined on each element of the partition in such a way that first we have to give a sigma algebra on the partition. So a set of subsets of our measurable space that are contained on the partition. So A inside P is measurable. This is the definition. If you take the function pi that takes each element on the space to the element of the partition that contains it, so a set will be measurable if pi minus 1 of A is measurable. So we have a way of defining also a measure here as the push forward of our original measure mu to this space, the push forward to P. So we have a way of measure things on the space given by the partition. And then this partition, when we take the measure and then decompose it with respect to this partition, this measure is taken into a disintegration or a system of conditional measures that satisfy these three conditions. The measure associated to element P of the partition calculated on P has to be 1 for almost every P of the partition, and this mu chapel is mu and this mu hat is the push forward of mu. This map that takes for each element of the partition a real number, that is the evaluation of a fixed measurable set on M, is a measurable function, and the more important part is this one. We can decompose the integration of a given set E or of a given function by first integrating using the conditional measures and then finally integrating using the transverse measure that is given this way. We call it transverse measure. And this is a generalization of Fubini theorem from calculus, in which we have an integral in R2, for instance, of this set A, or the volume of the set A can be measured by first we compute the volume on the horizontal. First we compute the volume on the vertical lines, and for each one of these lines we have a value of the one-dimensional volume, and then we integrate the result here. This is given by a double integral. So this definition of a system of conditional measures is a way of generalizing this concept of Fubini theorem to an abstract measurable space. And then we say that a foliation is absolutely continuous if the disintegration of the measure mu on the leaf, so mu x is mu on the leaf of x, of the Lebesgue measure mu. So we take the Lebesgue measure mu and we decompose it on a system of conditional measures, and we want these conditional measures to be absolutely continuous with respect to the Lebesgue measure on each leaf for almost every leaf. This is absolute continuity. this is an almost everywhere condition. So it holds for almost every leaf. And there's a strong condition that's the following. To define it, first I need to define the holonomy map. So, given a foliation F, we take two transverse local disks, sigma 1 and sigma 2. Let me draw it. So this is sigma 1 and this is sigma 2. And then to each point here on sigma 1, we associate the point on sigma 2, that is the intersection of the leaf that passes through the point key and through the local disk sigma 2. This is the holonomy map. And then the stronger version of absolute continuity is the following. We say that F is transversely absolutely continuous if given two smooth transversals, so that we can define the Lebesgue measure on them. Here and here. The holonomy map is absolutely continuous as a function with respect to these measures. That is the same that requiring that giving a set A inside sigma 1, if the Lebesgue measure of A is 0, then the Lebesgue measure of the image of A under the holonomy map also has 0 volume. So here in this picture, if this is A, if A has 0 volume, then its image under the holonomy map should also have 0 volume. And as I said, this definition here is stronger because I can take any transverse and the holonomy map has to be absolutely continuous. So it should happen to every leaf in a sense. And here this is an almost everywhere condition, so it should have for almost every leaf. So that's the reason this second definition is stronger than the former, and this is given by this result here. I'm saying this because in the proof that we are proving that our foliations that we'll construct in the following page, they are not absolutely continuous. But the kind of absolutely continuity they say in the paper, Michael and Amy, is this one. They say that the holonomy maps are not absolutely continuous. And to prove this is not satisfied is enough to prove that this is not satisfied. So we just need to prove that the conditional measures are not absolutely continuous with respect to the Lebesgue measure, or that there are a set with Lebesgue measure equal to 0 on the leaf, but the conditional measure of the same set is not 0. We are showing this, and then the foliation can't be absolutely continuous. This result in Michael and M's paper is part of a bigger result that has another conditions on the family of maps we are getting, but there are a simple version on Bonatti, Diaz, and Viana Dynamics Beyond Uniform Hyperbolicity book. And here this is the statement on this book, that there is a C1 open subset of C1 volume preserving partial hyperbolic maps of the three thoros, such that these maps are dynamically coherent, but these foliations are not absolutely continuous. This is what's proven on the book's version. And on the paper's version, it's a bigger statement that is the following. Given the Lebesgue measure on the three thoros, we can have close to a given linear partially hyperbolic map. So this linear partially hyperbolic map have a central foliation that is absolutely continuous. here the foliation is not pathological. So in the function, in the set of situ volume preserving functions of the torus, we have the map A3 here, and then nearby we have, as close as you want, open set U, and this open, with respect to the C1 topology, has the following property. For any G inside, G has these four properties. The first one is that G is ergodic and is non-uniformly hyperbolic, meaning that the Lyapunov exponents of G are all non-zero. And the second condition is that there is a fibration of the three torus that has the two torus as the base space, and the fibers are C2 circles, and they would be these C2 circles will form the center foliation. The third condition says that the directions that we use to define the partial hyperbolicity are ES, EC, and EU. In our case, the three of them are not trivial, and we are in dimension 3, so any of them has dimension 1. So the Lyapunov exponents are different because we have dominated splitting, so we have different exponential rates of growth in any one of these directions. So the Lyapunov exponents are ES, EC, and EU. And here we have uniform contraction, so the uniform expansion, so this is bigger than 1. Here we have uniform contraction, so this is smaller than 1. And the center one, in our initial map that is linear, it will be 0. And then we will perturb it and make it non-zero. This is the non-uniformly hyperbolic part. And this is robust. So that's why in the title we have removable zero exponents, because this zero exponent will disappear in a robust fashion. So getting back to the statement. So this center Lyapunov exponent, the intermediate rate of exponential growth, will be positive in this theorem here. So a direction in which we didn't have exponential growth, now we have exponential growth of vectors on the tangent space. This means that any vector that is on tangent to the center foliation, that is a tangent belonging to the center direction, will have this rate of exponential growth given by EC that is greater than 0. Oh, I'm sorry, this was 0 and this was 0. I don't know why I say 1. Anyway, and here the item 4 is the item in which we see the pathological part, that is the following. There is a set S of full volume that intersects each center leaf on a set of, with the volume leaf, a set of volume 0. That means that if we look at there's a bundle of circles over the two torus, in which there is a set S that meets each one of these circles on a set of 0 measure. So here is another set of 0 measure, and then when we join all these orange dots, they will give a full volume set of T3. This is what we call pathological here, because this is counterintuitive. Some remarks before we move on to proving the part 4 here. that is our focus in this video. The focus on this paper by Michael Schupp and Amy Wilkinson is on the getting robustly non-uniformly hyperbolic systems. But the maps they get here, this G here in particular, they are partial hyperbolic too. So they have a dominated splitting, they have a center direction, and in particular, this center direction has non-zero Lyapunov exponent. In this paper, they construct a family of perturbations on two parameters. This is a bit more complicated than what is done here on the Bonatti, Diaz, and Viana's book. But they do that because the parameters, the B parameter in particular, if you look into the paper, it makes the function G ergodic. So G is partial hyperbolic and it is ergodic. On the book, the focus is on the pathological center foliation, so they don't make the perturbation ergodic. The perturbation on the book, or the result given on the book ergodic, just by proving, for instance, accessibility, by this result by Burns and Wilkinson. If the maps have this property that we call accessibility, then we can apply this theorem and get that the maps here in this result are also ergodic. So with more modern results, we can get ergodicity in a more abstract fashion. But let's go to the proof of theorem, this theorem here, the book version, that is simpler and just focus on the part 4 here. Of course, we will also show that there is a non-zero Lyapunov exponent, and this condition will also follow. The only thing that don't follow in the book version is the ergodicity. How is the proof? First, we start with H, a linear volume-preserving anosis of diffeomorphism. So if it's linear, is given by a linear map on the torus. A linear map on the torus that is invertible is given by a matrix. Each entry of this matrix is an integer number. And the determinant of this matrix has to be 1 plus or minus 1. Because when this matrix has integer entries, so it preserves the class of X in the quotient, because here our torus is the quotient of R2 by Z2. So it's a well-defined function on the quotient, because the entries of the matrix are integers. And this map will be invertible on the torus because of this condition on the determinant. Because if it doesn't have absolute value 1, then it should be an integer number, and then the inverse wouldn't have integer entries. And then the inverse will not be well defined. So this condition is for the inverse to be well defined on the torus, because the matrix, if it can be invertible on R2 but not invertible on the torus if this determinant isn't 1 or minus 1. Okay, then this is an anosis linear map on the torus. And it has a eigenvalue of absolutely value greater than 1 and another one with absolutely value smaller than 1. And one of them is a direction with uniform expansion, and the other has an eigenspace associated, that is a direction with uniform contraction. And then we take this map H and define a product that is H on the first coordinate, and identity here is the identity on S1. S1 is R quotiented by Z. So this is a function on the 3 torus. And the derivative of this function, this is a linear function, so the derivative is equal to itself. The derivative of this function has 3 eigenvectors, and the eigenvalues associated are lambda 1 is smaller than 1, the center one is 1, and the unstable one is the inverse of lambda 1. And here you can check by the definition of Lyapunov exponent that I didn't give, but anyway, by the definition of Lyapunov exponents, that the log of lambda is the center Lyapunov exponent. The log of lambda is the stable Lyapunov exponent. The center Lyapunov exponent is 0, and the unstable Lyapunov exponent is minus the log of lambda for f. And we are going to perturb f. So the perturbation is given by f composed with phi. And phi here is, we give this on a different basis just to make the calculations of a following lemma easier, but I'm not doing the calculations anyway. And on this basis, we define the function phi as, on the second coordinate, that is regarding the center direction, we don't do anything. On the third coordinate, that is regarding the stable direction, we don't do anything. And on this the first coordinate, that is a combination of the center and the stable direction, we add something here, this psi, that depends on the center direction. So originally we had these 3 directions. This one is E, C, E, S, U. And then we are replacing this one here by this orange one here, that is a combination of the center and the stable one. And then on these 2, the gray ones, we are not doing anything. And on the orange one, we are adding something that depends on the center one. So here we are adding something. This will make the things on the unstable direction to remain the same, but the things on the center unstable direction would be a bit perturbed. And we take this alpha here to be a positive constant, and psi is a function from the torus to R that is C1 close to 0. We have to take a bit of care to define here, because this should be a well-defined function on the torus. But by taking this care, we can define it. And since this function here is small, is close to 0 on the C1 topology, then f is C1 close to G. So this will give, on the C1 topology, we have f here, that is the linear map. It makes the row of A3 on Michael and Emmy's paper. And nearby here we have a G. And by taking psi closer to 0, we can take G closer and closer to F, so as close as you want here. And then by that result that I mentioned at the beginning, the structural stability of the center direction, if G is sufficiently close to F, then G has a center foliation that is topologically conjugated to the center foliation of F, and the dynamics restricted to these foliations are also conjugated. Where is it? Here. So G is dynamically coherent because it has foliations that are homeomorphous to the foliations of F, to the leaves of F. that are circles. So the center leaves of G are circles. And then to finish the proof, we have to prove this lemma here. This says that if psi is not constant, this function psi here we use to add on the center plus stable direction. If this function is not constant, then the integrated center Lyapunov exponent, that is defined like this, is negative, strictly negative for G. And this is another difference because in here we have negative center exponent on Bonatti, Diaz, and Viana book. And here we have positive center exponent. But by taking the inverse, we have the same kind of map because we change the sign of the center Lyapunov exponent. And here, the definition of center Lyapunov exponent is like this. This is the definition. But here they replace it by something else. To do so, we need to check the following. This integrated center Lyapunov exponent of G is given by the integral of the Lyapunov exponent of G at the point x, and we integrate it over x. And this is the limit, the integral of the limit of 1 over n log of the derivative of G applied to a direction V that is non-trivial and is a center direction. And we can use the chain rule to open this derivative as a composition of maps on the center space. But the center space is one-dimensional, and these maps here are linear. So they have the same value on any point of the base. So this is a constant. This is a linear map, but in particular because EC has dimension 1, this is multiplying by a constant. So we multiply by a constant here and then here any times. So this norm here is, and MV is any vector. Its norm, its absolutely values doesn't matter because we are dividing by n and taking the limit. So by taking v of absolutely values 1, we have that this integral is the integral of this value here, that is the constant that is defines the linear function of dg over this one-dimensional space here, to n. And then this n comes out of the log and is cancelled. And then this integrated center Lyapunov exponent is just the integral of the derivative of g restricted to the center direction. And then this is good because this implies continuity. That is, lambda c depends continuously on f, lambda c of g, because g is nearby f. The reason is the following. This function here, that for each f on the space of C1 diffeomorphisms of T3, for each f, this is the composition of the tangent space, the tangent bundle of f in a center, stable and unstable bundles is continuous. Each one of these bundles is a line bundle, is one-dimensional, and it depends continuously on df. And df itself is continuous because the map is C1 and volume preserved, because the map is C1, and it depends continuously on f because we are in the C1 topology. If f is C1 close to G, then df is C1. Then, for short, if f is C1 close to G, df is close to dg, and the bundles EF for sigma here being either stable, center, or unstable, for f is close to the corresponding one for G. So using this lemma here that says that the center Lyapunov exponent of our perturbation G is negative, we have that since this is continuous on G, this will be negative on a C1 neighborhood of G. So as I said, we started with F, we have G as close as we want, and then we have a neighborhood around G for which everyone on this neighborhood have negative Lyapunov exponent. Of course, this neighborhood should be small enough so it doesn't contain F, because F doesn't have a negative Lyapunov exponent, the center Lyapunov exponent. The center Lyapunov exponent of F is 0. But anyway, but if the Lyapunov exponent of G, the center one, is non-zero, in particular in this case, if it's negative, then there should be a set E inside the three-dimensional torus with positive volume such that the center Lyapunov exponent is smaller than 0, because this center Lyapunov exponent is the integral of this thing here. So if the integral of something is negative, this something should be negative on a positive volume set. But the foliation WC is a foliation by circles. So we have a continuous family of circles over the two-dimensional torus. And then the lengths of the circles should be bounded, because it's a continuous function over a compact space. They are uniformly bounded. But this foliation is also invariant by our dynamics. So any circle is taken by the dynamics to another circle. Each one of these circles have bounded length. So this family here, when we take one circle and we start to iterate it, they are all circles inside the same family, and they all have bounded length uniformly, because it doesn't depend on the original circle we take. Therefore, we can't have inside the circle segment lambda that is also on E and has positive length, Lebesgue length, inside the circle. Because if we had it, we should have an interval inside this curve here, and this interval has to by taking the negative zeta rates of f, its length should grow exponentially. But it can't grow exponentially because it's restricted to a circle with bounded length. So this can't happen. So E inside each center leaf, that is inside a center circle, can have a positive length subset inside the circle. E can't meet the circle on a positive length set. Now, if we suppose that the center foliation is absolutely continuous, then as we take the measure mu and its conditional measures regarding the center foliation, then by the definition of absolutely continuity, this conditional measure should be absolutely continuous with respect to the Lebesgue measure for almost every leaf. This means that the Lebesgue measure restricted to the leaf of a set A is 0. This implies that the conditional measure of the same set A is also 0. And here I explain again what is this transverse measure. That is a way of saying almost every leaf. Right? So there is this projection that takes every point of the torus to a center leaf, and this function induces the sigma algebra on the space of leaves on the foliation, as I said. And we have a measure here that is the push forward of our original measure. So I have already explained it. This is the explanation of this measure here on this context. Anyway, but by the definition of the disintegration, the volume of our set E here, that should be positive and should have this function here negative, this E, its volume is the integral over the partition of the integral over the leaf of the volume of E inside the leaf. This is the measure on the leaf WCX, and this is the transverse measure. This is the definition of conditional measure. And then, since our set E should have positive volume, then there must exist a positive set of leaves, so a positive set inside the partition with positive transverse measure, such that this set, for this set Q, leaf inside this set should meet the set E on a positive volume measure regarding the conditional measure. But the conditional measure is absolutely continuous with respect to the Lebesgue measure on the unstable, on the center leaf. So this set here should have positive Lebesgue measure, but we already saw that this can't have positive Lebesgue measure. So this is a contradiction, and WC is not absolutely continuous. In particular, is not transversely absolutely continuous. The holonomies are not absolutely continuous functions. And this concludes the proof minus the lemma that I didn't prove. And actually, we can see that this foliation WC, not only it is not absolutely continuous, but these conditional measures here are atomic measures. This is the content of the paper of Ruel and Wilkinson.